recording the lecture. And again, I am recording via OBS because that seems simpler. Now, a couple of things to, just administratively, exams will be Friday. I'm going to send out an announcement. I'll probably host the exams rather than your TAs and mention for your TAs to be there. So your exam's on Friday. It will be online. And you should study for it. But again, it's pretty open. Open book, open notes, open laptop. You can use the IDE if you want. I'm going to be doing it on Canvas. If you need extra time, because of DRS or something like that, or other accommodations, let me know. Otherwise, it's going to have a 2-hour, window for you to take it. I'll be online to moderate the exam and have answer questions with it. So, so that kind of thing can, so you can help with that kind of thing. So I can help out and answer questions that kind of way. But it's essentially just going to be a longer quiz on Canvas. I'm going to be using the new format for that because it seems to be easier for typing in formatted text. You use I think I'm going to have to do a video on how to do the pre-formatted text. Just so it's like going to take it's a 3-minute thing to learn, but it's better for you to learn it now than later.
Will we be able to just copy and paste from an IDE?
Yes, you will be able to copy and paste from an IDE. And that's why I highly suggest you use you want to use the formatting tool, which I'll show you guys in a separate video. Or I'll do a 3-minute video so I can send it to both 1051 and 2168. But the idea here is I want you to be able to copy and paste to an IDE because that makes sense. From an IDE because it makes sense to do that. The questions won't necessarily account for you having an IDE in the sense that, I'm not going to necessarily provide a simple node class for you or necessarily a way for you to test your code. So I think that's the fairness involved in it. So if you want to come to class prepared with your own node classes or your own binary search tree classes, that is fair enough. But otherwise, I'm not going to provide I'll show you actually. Screen 1, right here. Practice. Here's the practice exam, which I'm going to go over in more detail today. Right. If I provide you this, I'm not necessarily going to provide you I'm not going to provide you the class or the node. But if you can use the ones that we've done in class previously. So if you want to come and be prepared for that, you can. Also, any other questions about the general way the exam will work before I go over the specifics of the exam? And this isn't a speak now, forever hold your peace. You can ask questions later if you need to. Because I want to go over this. Now, if you've taken a look at the practice exam, you'll have noticed, well, first off, I wasn't able to squeeze in the extra 5 points where I wanted them to be, but it'd still be out of 5. You'll notice that of the questions, we had 12 here, 12 here, we had 24 points for so we had 24 points for tree questions, and then another 10 questions for the count method. So you can expect somewhere between around a third of the points are actually coding for this exam, as opposed to being much coding, as the previous exam was was coding heavier, right? This exam is going to be more coding light, and actually I'm going to be putting in the questions online today in basically an easier way. Like here, draw the binary search tree that forms after inserting the following integers. I mean, I could do that, have you do something like that. I don't know. Would everybody be up for doing a file upload? Like drawing something and then either taking a picture and uploading the file? Or that seems like it's just a bit much extra overhead, in my opinion.
From my experience, the file uploads don't work. Like when I uploaded mine, just nothing showed up in the PDF.
So there's a response. Because the other question I think I'm going to do for the style question I'm going to do for this is, let me go ahead and, there's a question, there's, here, let me go ahead and grab it because this is a practice final I use. All right, so this is a fairly good multiple choice question. The binary search tree shown below is constructed by inserting items of sequence into an empty tree. Which of the following input sequences would not produce this binary search tree? So I think that's a pretty fair question for a pretty good multiple choice question that tests you on the same thing. So, for example, this question would be, well, so 5, 3, 4, 9, 12, 7, 6, or 8, 6, 12, or so 20 works. So A works, that's fine. B produces this same tree as well, 5, 9, 3, 7, 6, 8, 4, 3 was already done, 12, 20. Same thing over here, 5, 9, 7, 8, 6, 12, 20, 3, 4. And what about this? And we check this one as well, and it will be fine. But if we check E, we notice that 5, 9, 3, 6, then 7. So if we added the nodes to this tree in order, it would produce a completely different shaped binary tree. Everybody kind of understand that? Did I confuse anybody on this one?
No, I get that.
Yeah, so I think it's a fairly good way to test that, to kind of test that one. So those kind of questions. So basically, I'll just try to make this as adapted for this as possible. All right. So with that, let's go ahead and go over the practice exam. So your first question will be this, which is basically, here are the data structures we've learned so far. Please tell me which ones. Oh, and by the way, before I get any further, let me post the next homework, and I will go over that on Wednesday in more detail. But this one's meant to be a much light. Oh no, they're already posted. It's just I haven't adjusted the due date. I'll figure out the due date for that. But the sorting assignment is one of those funny assignments where I explicitly say, hey, you can totally copy-paste somebody else's code you found on the internet because you're going to have to make adjustments to it anyway. Here, I'm less concerned about you guys creating the sorting algorithm and more about collecting data, right? So that's the objective of the sorting algorithms assignment, which I've given. It's all about collecting data. So I'll actually probably going to amend that one a bit just to go into more detail about that. But it's not meant to be. It's this. Just be sure to watch the sorting videos. It's not going to be on the exam, on this exam. It will be on the final. But this is designed to be a much, much lighter kind of deal. So let's go ahead and go over this. So you need to model which patient should be seen next at a hospital. Geez, that's more prescient now. That's contextual now. Wasn't when I wrote this question though. You need a model of which patient should be seen next at a hospital. Patients should be seen in as close to the order of arrival, but patients with more severe situations should be seen first. So what data structure models this?
Priority queue.
Yep, a priority queue, because that allows people who need to move to the front of the queue to do so. What data structure is a priority queue built with?
Heap.
Yep. A router needs to hold packets in a buffer and deal with them in the order they appear.
Queue.
Yep. You want to model some kind of hierarchy.
Tree.
Yep. Trees are all about hierarchies.
Wow.
And you need a data structure to hold your previous decisions in case you need to backtrack.
Stack.
Yes. So, for the record, recursion is not a data structure. It is a technique. And on the final exam, the questions are phrased a bit interestingly. And so I have sometimes students who are like, "Oh, that's a maze, so I use recursion." No. Stack. You talk about the data structure. So tree relations and vocabulary. This will be on. So there's going to be a page. It'll be worth about 10 points on the on basically just terminologies for the tree for these. I'll try to auto-grade it as good as possible, but it's possible that you put something in and it's correct, but the auto-grader marks it wrong. That's okay. I'll just have to manually correct that myself. So the node at the top of the tree is called the what?
Root.
Mm-hmm. The links from nodes to successors are called what?
Branches?
Yep. I'll also accept links because, language.
Would
Nobody's
you
going to
accept-
care.
Do you accept edges as well?
I will
since it's
accept
a
edges.
typograph? Cool.
If you were going into an interview and the word you use makes sense to the interviewer, then I accept it.
Rad.
The predecessor of a node in a tree is called what?
Parent.
Yep, the parent. Also, I'll take the ancestor, but even though that's more generalized. Nodes that have the same parent are called what?
Siblings.
Yep. By the way, if what is my parent? Well, who's my parent's sibling?
Your uncle.
Uncle or aunt? Don't really care. We don't have, and interestingly enough, I haven't figured out a gender-neutral word for that because we have parent, we have grandparent, but we don't have a gender-neutral for that. So that's kind
Cousin
of
parent.
what?
Cousin parent.
Cousin, parent, cousin.
Yeah.
Describe without using code how to calculate the height of the tree recursively. So, the easiest way to do that is if you're talking. So, if it's recursive, then it's all about local decisions. So, the height of so rather than thinking about the height of the tree, we think about the height of the subtree. So, I'm the root of a tree or a subtree, and what I need to know is what is my height so I can return it to whoever called me. Well, my height is, I know since I exist. Well, first of all, if I don't exist, my height is 0. If I exist, then my height is 1. And then it's 1 plus whichever is bigger. The left side of my tree or the right side of my tree. So, 1 whichever's bigger, the left side of my tree or the right side of my tree. So, and there is a I'll type it out in chat. A math.max, you don't even have to import it, but given if I were to type in 5 and 10, it would return 10. There's also a math.min function. Don't know if you knew that. It's just a nice little function built in that we could honestly live without, but it's nice that it exists. This page will be a bit different when I'm on the exam, but it will be covered the same material. Basically, I'm going to say, hey, here's a tree. And I'm going to ask you a bunch of questions about this tree. So node A and what is the relationship between node A and B? What is the relationship between node D and B? If you remove what happens to the tree or like what needs to happen to this tree to make it complete and things like that. Speaking of which, draw an example of each of the following types of binary tree, which we won't need to do on the exam. The reason I use a different example for each possible tree, and let me go ahead and share, and it's full, complete, and perfect. So I'm just going to switch to the whiteboard for a second. Give me 1 second to switch. To get out my. Give me 1 second. Sorry. Okay. And where's the pen? Oh, there it is. Okay, switch to the whiteboard. If I got this thing, I might as well use it. Okay. So the reason I specify we need to do different nodes for each tree or different trees for each thing is because this is full, this is perfect, and it is complete. So let's go over full first. What is a full tree?
Everything either has 0 children or 2 children, I think.
Yep, that's exactly it. Everything either has 0 children or 2 children. So, over here, right, boom. Okay. So this is full. Everything either has 2 children or 0 children. Everything's either a leaf or it's got both its children, right? This would not be full, right? Because this node over here now disqualifies it. This node now disqualifies it. Because it is, because it has 1 child. If it's full, that's full. Okay, that's full again. Okay. Any questions about full trees? I don't think so because they're the easiest to understand. Clear. Okay. Next is, let's go with a thicker line too. All right. Next is next was complete, but I'm going to do a perfect next. A perfect means basically if it's of height h, then you have 2 to the h minus 1 nodes in it. That's the mathematical definition of a perfect tree. That's binary. Which means that basically it's made up that it's going to look either like this. So height 2. So this is height 2. It has 3 nodes. This is height 3, so we'll have 7 nodes. 2 to the third, right? 2 to the third minus 1. When you drew these questions, can we just draw the nodes as circles? Yes. Unless there are numbers, unless we need numbers, like, but honestly, I'm going to try my best to make it so you don't have to draw anything. Because that seems a bit time consuming and there could be a technical difficulty there. But here, right, we've got 1, 2, 3, 4, 5. So this is a perfect tree. Because basically you can think of it as basically kind of a mathematical example for a tree. This is not perfect because it is height 4. So a perfect tree of height 4 would have 2 to the 4th, which is 2, 4, 8, 16, minus 1, 15 trees. There are 15 nodes in it. This one only has 9. So a height 4 tree, and as you might imagine, because each node has 2 children, it gets quite a bit crowded as it goes on and takes twice as long to draw each level. Okay. Now, a complete tree is one that is perfect up to a certain level. It's this next level that has an interesting rule that really doesn't fit, but it's useful for heaps, which is that these first 2 levels are complete, but this bottom level over here is filled in as far as possible left to right. From the left to the right with no gaps. So let's draw this again. This is complete. This is So notice the order I am drawing things in. That is the I'm slowly incrementing 1, tree one node at a time to keep it complete. Now, if I were to draw a node over here, that makes it's no longer complete because this guy was missing 2 children. If I draw this guy over here, and to be more explicit, I'll draw an X over here to show that it's null. This is not complete because we have a gap here. Right? We have a gap here. If, on the other hand, we had this is a complete tree. Any questions? Also, if this wasn't here, this would no longer be complete as well, because this part is no longer perfect. So, any questions about these tree definitions? On the exam, the questions are going to be like, given... okay. Whoops. So, the question on the exam might be something along the lines of, you know, given this tree, you know, what nodes have to be removed to make it complete? Or add nodes to make it complete. That kind of deal. So that might be that. So basically, I'm going to try to make it as easy again to answer with just being able to select stuff on the computer screen. Let me share again on screen 1. All right, so let's go and continue. So tree operations. Draw the binary search tree that forms after inserting the following integers. 42 inserted first. I'm gonna now I always forget how to, yeah, Edge isn't that great for that. So let's go ahead. I'm going to go ahead and work through this right here because I can't memorize all those numbers. So let's see. We're going to start out with 42. And then 10 gets added next. And then 50. And then 12. And then, let's see. So 17. 17 is, let me go ahead and draw. Oh, that doesn't help at all. So, clear. Draw. I need to draw smaller on this. So 40, which is hard. 42, 10 is less than 42, so it goes to the left. 50 is greater than 42. So it goes to the right. 12 is less than 42 but greater than 10. So it goes over here. 17. 17 is less than 42, greater than 10, greater than 12. So it goes over here. 80 is greater than all those. So it goes all the way to the right. Negative 12 is less than everything. So it goes over here. 100 is greater than everything we've seen so far. 196 is greater than this, greater than this, greater than this, less than this, so it goes over here. 105, 86, and then 72. Yeah, greater than this, less than this. That's why it ended up there. Any questions on that one? Okay. So, mouse. Using the previous answer, draw what happens when you remove the following. Arg. Completely forgot. Undo. Hey, that worked. I feel very clever for doing that. Alright, draw what happens when you remove the following. So remember, for remove, what has to happen is that it depends on how many children you have. If you have one child, if you have no children, you just remove it. if you have one child, you have your parent adopt. If you have two children, and you find your next in order predecessor, and then you reduce to as simple as to one of the other cases. So 42 means that we need to find our next in order predecessor, which is 17, and we're going to move it up here and we're going to replace ourselves with our next in order predecessor.
Sorry, can you explain why it's 17?
As opposed to what? 40?
I don't know.
Okay.
86?
Because with 86, we'd have to basically restructure the entire tree, right? If I were to put 86 here instead, right?
Yeah.
Then we would have this whole... Then basically, this would no longer be correct. This would no longer be correct. We'd have a bunch of stuff that's no longer correct. So the next in order predecessor is this thing that is the largest thing that is smaller than me.
Okay.
So it will
Thank
be
you.
smaller than everything over here and bigger than everything over here, so it fits perfectly as the new root. That's why we find it. The same would be true for also the next in order successor, but I like to do the next in order predecessor. So to find it, you find the biggest thing in your left subtree, which is actually fairly straightforward. You go into your left subtree, so you go one step to the left and go all the way to the right. So that's how we find 17. And we know it's the biggest thing in the subtree because if we went left, we would have been in something smaller. And if we could go right more, well, that thing would be bigger. But there's nothing more to the right. So what we do is, again, we're going to just simply take 17 and replace 42 with 17. Okay. And next is, the next step is to remove 12. 12 is easy enough to remove because guess what? It's just one, it has no children. Oh, this has to be removed with, sorry, I said 17 over here. Almost 17. We remove 12. Now we remove 17. So here we need to find the next in order predecessor of this. The next in order predecessor, you go one to the right, one to the left, and go as far right as possible. So that would be 10. To delete 10, so we're going to put 10 up here, and then we're going to delete the original 10. And the way we do that, to delete the original 10, is that we have 10's parent adopt its child, which means have the root adopt its child. Okay. Then finally adopt 96. Again, what we do is that we delete 96 over there by having it 96's parent adopt its child. Make sense? The hardest thing you have is when you've got basically, when you go to one, or the one that feels the weirdest is when you go one to the left and you go as far as you can to the right and you don't end up anywhere different. That feels the weirdest, but just remember those rules and you'll be fine. So which of the following is the preorder traversal for a binary tree? Preorder means you handle yourself first, then your left subtree, then your right subtree. So BB. Post order means we handle the left subtree, then the right subtree, and then ourselves. On the exam, expect to basically be given a tree and asked for which is the correct output, or to give me the correct output for the tree. So for heaps, again, it'll probably be a question similar to the tree. Draw the min heap that forms after inserting the following integers. So first thing we would do is 8 and then 10. Notice that goes to the left because basically we're creating a complete tree. And the heavier items, they sift down. Heavier items fall to the bottom while the lighter items bubble up. So 8, 10, 50. The next is 20. So, right, 8, 10, 50, 20. Then we've got 1. So 1 is lighter than its parent, 10. So it's going to bubble up. While 10 is, so 1 is going to bubble up while 10 goes down. And then we continue. 1 is lighter than its parent. So 1 bubbles up here. And 8 drops down. And 1 can't bubble up any further, so we're done there. So next I had 4. 4 is less than 50, so 4 will bubble up. And by swapping with 50, its parent. $54. And again, if I'm greater than my parent, I swap with my parent. Sorry, if I'm less than my parent, I swap with my parent. But I'm not, so that's fine. And then finally 3. Let's add 3. Am I less than my parent? Yes, I am, so I'm going to swap. You're going to be doing a lot, you would probably have to do a lot of erasing on this one, as you noticed. Using the heap that you drew above, draw the heap after removing an element twice. So first off, whenever you remove an element, what is the item that gets removed? Yes, we have an answer, and it's probably the correct one. The root! The root of the tree. That is the correct answer. Now, let me change the question a bit. Now, with this heap, if I'm going to do a remove operation twice, what's going to be the new root of the tree without having to draw it? Can you tell me? You can. What's going to be the new root of the tree if I remove twice from it?
4.
Yep. And the reason we know that is because if I remove an element, if I remove an item from the tree, I'm going to remove the smallest item. And if I remove again, I'm going to remove the next smallest item. So if I do a removal, it'll be 1 and 3, and then we know with the way a minimum heap works, the smallest item will always be the top. So if I remove twice, the item will be the item on the top will be 4. But how do we get there, right? How do we get there? No shortcuts. Well, so let's go ahead and remove the heap. To remove the item from the heap, what we do is that we take the last item in the heap, the item in the last position, and move it to the top. Remember, we do that so that it's going to stay. We have to do that because otherwise the heap will not stay a complete tree. And that's important for this. So now we've got 4 moved to the top over here. So now we need to basically reheap, or we need to fix the heap. So we do that by saying, hey, if I'm bigger than either of my children, I swap with the smallest child. So here 4 is smaller than 3, so it's going to swap over here. Yeah. Let's go ahead and just delete these. 3, 4, right? Okay, next. 4 is smaller than 50, so we're going to just keep, so we've hit it as small as we can, so we're not going any further. Next thing we do, the second item we delete is going to be 50. So we are going to take 50 and move it to the top. 50. And now we push, and now again, I'm bigger than both my children, so I need to fall down. But I'm going to swap with my smaller child. So I'm finally making good use of the Wacom tablet, by the way. Sorry, so 50 and then 4. Okay, and that would be the result of the heap I drew twice. Now remember, the way you can know if the heap is a correct heap is that we have is that the root of a heap or subheap is always smaller than its children. And that is a recursive process as well. Okay, next. Keep moving. Huffman Coding. Okay. So why did the numbers fall the way you did when I built the heap? They fell the way they did because the numbers always, when you're building a heap from the bottom, by adding an item one at a time, the smaller items bubble to the top, and the heavier item, and they swap with their parent to do so. When you are deleting a node, right? You take an item from the bottom, put it at the root place, and let it fall to the appropriate place. And what you do is that when you delete an item and put that big node on top, is that you have to ask, am I bigger than either of my children? If I am, I need to swap with one of my children. And the way that it's going to be the most correct is that my smallest child has to swap with me. What determines if they fall right or left? If the right is smaller, it swaps with the right. If the left is smaller, you swap with the left. Because if we were to put for instance, if I were to have that's not going to work. That's drawing a line. Okay. So for instance, if I were to have 50, 8, and 4, if I were to swap with the 8 would go up here, but 8 would be bigger than 4, so that would be incorrect. Right? 8 would be bigger than 4, so this wouldn't be a min heap anymore. So I swap with the 4 instead, so that it stays a minimum heap and I can swap again. So right or left just determines on what was there. If it was, and it could just as easily be this way: 4, 8, 50. So we need to swap this way. All right. Huffman trees are, let's see. Huffman trees are fun, even if they are a bit of a pain. But they are on both this exam and the final exam. So, and they're important. So, first thing we need to do is we need to draw our priority queue. Or create a priority queue. X1. Let's put them in order of appearance. X1, L20. P40. A50. And E60, with this being the front over here. So they're all in order now. So to draw a Huffman tree, what we do is that we take the two symbols from the front. The first symbol becomes the left, the second symbol becomes the right. So X and L. Okay. X, L, and they have a combined weight of 21. Okay, and then we reinsert this new node back into the tree, or back into the priority queue. And because 21 is smaller than all that stuff, it's going to go right here, 21 XL. Next, we dequeue these two guys. XL and P. XL goes on the left because it was first. P goes on the right because it was second. P. XL goes on the left, right. Had a combined total of 61 because this was 40, this was 21. So next we put this back in, and it's going to go here because XLP has a combined weight of 61. Next, we dequeue the next two. Let's see. So, yeah, that was 120. Yep. So, next is A and E. We dequeue those guys. So, they had 50 and 60 respectively. A had 50, and it was smaller, so it goes to the left. A, E, 110 combined weight. Okay, and then that gets added to the queue. And now we've got to combine XLP with A and E. Left, right. Combine them into one tree. And now it's the only thing left, so we're done.
Wait, Professor Risen.
Mm-hmm.
Why do you do like the 110 on the right instead of just moving up the 61 thing? If that made sense at all.
So the reason being why we did AE the way it did is because, or why did AE end up by itself rather than adding it onto the tree over here?
Right.
Because A and E were what was next. XLP. So this guy was completely left out because from this step because he wasn't one of the two nodes in there, right? Really, it's it's AE and 61, right? If you might think of that way.
Gotcha. That makes sense.
Isn't it because A and E were both previously unadded?
Yep, A and E were previously unadded, so they get added to a new tree together, which will eventually get added, which got added to the tree eventually, like that.
Do you leave like the numbers in the tree when you're
You
done?
don't have to. What's important is the symbols, not the what's important is our leaf nodes. Like, so it doesn't matter. So I can just leave this blank. Now to encode Apple, we put zeros for the lefts and ones for the rights. So Apple in this configuration would be 1 0 and then two P's. A P is 0 1 0 1 0 1. And I'm just going to split it up like that for myself. A P P L E. That doesn't work. A P P L E. L is what? 0 0 1. L. And X. No. E. E is 1 1. So now, if I send this to a... So that's our answer. Now, if I were to send the tree and the message to somebody, they'd be able to decode it. So if I sent just this message... And
I have a question about your tree.
Uh-huh.
Why was P on the right of... Never mind, I got it. Sorry.
Mm-hmm. So I'm just going to clean this up a bit. We're just going to clean this up a bit. So if I sent... Sorry. If I sent this tree to whoever I'm communicating to, then they would mark it themselves and go 0 0 0 1 1 0. They could basically go through and say, okay, I'm starting from here. I see a 1, I see a 0, so that, and I hit an A. So 1 0 over here gives me an A. So now I read the next bit, and I see 0, then a 1, so I see a P, and a 0 and a 1, so I see a P, and then I see a 0, and then a 1, So 0, 1 doesn't mean P. 0, 0, then followed by 1, that means L. And then 1 and 1, that means an E. I see Apple. All right. Any other questions about that one? Okay. Coding. Move that. So, write a method which, given the root of the tree or subtree, computes and returns the number of nodes in the tree or subtree. You may not use the size method. Forget that it even existed. So, I'm just going to grab this. I'm not going to bother booting up a full IDE for it. This is one of those that you can answer in basically one line if you, aside from the method statement itself, if you know what you're doing. Care what it is because I just really want the syntax highlighting. Okay. So, we've got public static E int size tree. So we want to figure out what the size of this tree is, or more specifically, we're writing a method that computes the size of this tree or subtree. So all the decisions need to be made local. So first thing we want to ask ourselves is if return 0 for right now and first see. It is not liking the fact that I'm outside of a class, so public class exam and that should calm it down somewhat. So now if root equals null. So that should be our first check. What if our root is null? What if our root doesn't exist? What is the size of the tree if I don't exist?
0.
Yep. If I don't exist and I don't have any children, so I know that would be 0 on myself. I don't exist. Otherwise, what the total size would be, let's see. Otherwise, the total size would be composed of my left subtree size, my right subtree size, and my own size. So int my size is equal to 1 because I am one node alone. My left subtree is equal to, it's equal to root dot left, calculating the size of that. Which, if I don't have a left child, that's just going to return 0. And if it's the full, and otherwise, it's going to compute the size of its it's going to figure out what the size of the tree or subtree is. Right. The size of root dot right. There we go. Oh, it's called size tree. Whatever. Okay. So int my size, and so return left plus my size plus right. This makes sense to everybody so far? Okay, if you wanted to be really sneaky, you can condense it into this, which is size tree root dot left and I'm probably not going to run your code to check if it works. I'm probably just going to read it because that requires me copy and pasting, and I can just kind of read it. So size tree root dot left, my size plus root dot right. Okay.
I have to change my size to 1.
Yeah. Gotta change to 1. And that condenses that answer even more. And if we really wanted to condense our answer, we could do return root equals null question mark 0 colon that. Which, if you notice, it stopped complaining about that and accepts that as appropriate syntax. What messed up arcane Cthulhu crap did I just put there? Anybody know what this is called? This is what we call a ternary operator. So what I've done is that it's basically an if-else statement in the... it's basically an if-else statement in one line. So it's saying... so you put a boolean here. If it's true... And then... Sorry, you put a boolean and a question mark. If the boolean is true, you do the stuff before the colon. If it's false, you do the stuff after the colon. These are annoyingly hard to read, so you just don't, so it's much better to do this than to show off. Okay, but possible to do that one in one line is the point. Next one is full. Write a method which, given a tree, returns whether the tree is full. It will be slightly different than the recursive traversal methods we've tried so far. So, right, if it's full... So first off... okay. So let's just check. So we need to start off, is full... I'm going to change this to root because I can do that. If root equals null, return true, I guess. We'll figure that one out when we get to it. Okay. But I have to check if I exist, right? But now, actually, if I'm checking to see if I'm a full tree, I have to actually care about the existence of my children, right? Here, in this one, I just kind of left the fact that I have children up in the air. Here, I actually have to be a attentive parent and, you know, figure out, wait, do I actually have kids?
Yes, you do.
Yes, I know I do. So, no. So first, so what we're gonna do is basically, okay, if this, and again, this is if this subtree or subtree is full. So first off, if root dot left equals null and root dot right equals null, right? If I don't have a child on my left and I don't have a child on my right, I have no children. By definition, I am full, right? Everybody agree with that? If I have a child on my left, and I have a child on my, if I have no child on my left, no child on my right, then great. I am full. However, else if root dot otherwise, though, if I have a left child but not a right child, I need to return false. Make sense so far? Please tell me if I lost you. So if I have one child but not another child, right? A tree has to have, so a full tree has to have every node either has 0 children or 2 children. And if I only have one child, I can't be a full tree despite anything else that's going on. Okay. Otherwise, and the same goes for the other side, right? This is just this, but right and left have been swapped. If I have a right child or left child, I gotta return false. But if I have both of my children, well, okay, that's great. I'm an interior node now. So this actually makes it a bit tricky now. Because, actually, I gotta figure out, I'm only a full tree if my left subtree also is full, and my right subtree is also full, right? If neither of them are full, that means that one of them broke one of the tenets of having either 0 children or 2 children somewhere in their tree. So my whole tree can't be full. Some kind of blood purity bullcrap in there. Could you just check if the node has 2 children or 0 children and return false otherwise? I mean, yes, but then we need... So here, we need to do a recursive blood purity check of some kind. Shaking my head.
That's a reason.
Yeah.
Why couldn't we just check if the root.left not equal null and root.right equal null, and then another one to check root.left equals null and root.right does not equal null, and then if both of those, if either of those are true, just return false. If not, return true.
Because we
All
need to do
else.
something a bit, because we actually have to do a bit more over here. We have to check if our children are full. So, here what we have to return is return is full So here, in this case, right, I could just return true over here because I knew I had no children. So there's nothing left to check. But over here, this is our recursive case. So these are all base cases over here. But once we can no longer make a local decision, basically, I can make, by local, I mean, I can make these decisions without having to really ask the nodes anything else. Having a left child and a right child, those are attributes of mine. So I can check them myself. But as soon as I have to ask, wait a second, is my left subtree full? Is my right subtree full? Do I have to check the rest of my tree? That's when I have to make the recursive call. So I'll give you a small hint. I like doing properties of trees on the exam because they're pretty interesting. But I'm not going to ask you if it's complete because that would be annoying. But, so I think these questions are good. Equals map. Yeah. So I think I have time to do... I'll back up the equals in a bit. I want to just do the next... I want to do this one. So... My cat has just been meowing so much. Do the cats have food, Annie?
I thought so, but I'll check.
Mm-hmm. Alright. Let's go ahead and put this over here. So here, we need to... I want to return a count of the characters that occur in this string. So write a method that returns what characters occur in the string and how often each one occurs. So, for this one's fairly straightforward and very representative of the kind of question you'll get concerning maps. For character C in Python, word dot to character array. And you got to do that to do a for each loop on this sucker. Next, what do I need to do? Right, I need to make a map to actually return things. Map, character, integer. Map is equal to new hash map. Don't worry about importing anything in your answers. You can assume that it's imported. Map is equal to new hash map. Great. Now for character in the character array, map dot So if map dot contains key, if we've seen C, so if we've seen, what we're going to do is that we're going to go through every single letter in this word. If our map, which is going to be used to count the characters, has seen this character before, then we have a previous count. So we're going to get our previous count. Int count is equal to the map.get the number of times I've seen it. So if I've seen it before, get the previous number of times I've seen it, and then replace that with having seen it one more time, right? So if I've seen this character before, I get the number of times I've seen the character, and then update that entry by adding 1 to it. Otherwise, this is the first time I've seen it. So map put C1. Methods like this for maps are very easy and very standardized to write. Basically, if I haven't seen it before, then I've seen it now. Otherwise, add 1 to the number, get the number of times I've seen it, add 1 to it. It is totally possible to just simply do this instead. Map.get C plus 1. But I know that basically that on an exam, you probably want to keep your nested parentheses to a minimum for ease of readability. Okay. I'm going to do the analysis, and then I'm going to do the extra practice question. We can skip this for now. What are collisions in hash tables? Why do they occur, and how are they handled? So a collision in a hash table is where we create an entry for a hash table, right? And so we create an entry for so we try to put something into a hash table. But the index that we get hashed to is already occupied. And this happens because we are mapping keys to indices, but our hash table is smaller than the universe of all possible keys, which is every single possible number out there. So we reduce that to a smaller table, so things are going to collide with each other because multiple keys are going to be mapped to the same index. So how are they handled? They are handled in a whole lot of different ways. One way that you can handle them is open addressing with linear probing, which means, hey, if I'm trying to put this key value pair into a slot, and my slot is occupied, which is a collision, then I'm just going to take the next available slot. That's all. And next available is defined as I look literally one index over, and if that's occupied, I go look one index over from that, and if that's occupied, so on and so forth. If I have to wrap around, I do. There's guaranteed to be an open spot because we'll be resizing if we need to. And as soon as I find an open spot, I'll take it. In open addressing with quadratic probing, next available is defined by using a quadratic method. So from my initial spot that I tried to go to, I look one space away. Then I look one squared space away, which is one space away. Then I look 2 squared spaces away. Then I look 3 squared spaces away, and so on and so forth. The advantage of this is that it gets more spread out. Disadvantage of this is now I'm adding a multiplication operation into the calculation, so it's just a teensy bit, and I held up my fingers, but of course I really wish that he would hold up his paws. So just a teensy littlest bit longer. Another way of handling it is chaining. That's a very, very popular method. And what that means is that we can is that basically each slot is a linked list. So if there's a collision, you just add it to the linked list in that index. And to find an item, you just simply sift through the linked list. And you resize when the average length of a linked list gets too long. There's also something called Cuckoo Hashing, which Brendan is very fond of, our guest speaker from Wednesday. And that's simply that if a space is taken up, if your space is taken, look for, you try an alternative space. And if your alternative space fails, well, then you kick the person out of your alternative space, and then that person goes and looks for their alternative space and kicks whoever is out of there, and so on and so forth until everybody finds their space. This is named after cuckoos kicking birds out of nests. All right. So what is the worst case runtime for the insertion and deletion algorithms of a binary search tree, and why? So what is the average case for insertion and deletion? Anyone? What is the average case for inserting and deleting? If you're saying something, your mic is muted, but I'm not. Yay, log n. Okay, average case is log n, which I'm going to remind you is log base 2 in computer science. The 2 is assumed generally, of n for average, right? And that's because we have our choices each time on average step. But a worst case for insertion and deletion for a binary search tree is if we end up with a tree that's shaped like this. Each time we go down a branch, the most all we're eliminating is one other node, right? Over here we eliminate one node. So it's essentially a linked list, which means that the worst case time to insert something into this sucker is O of n, and the worst case time to insert something into this or to delete something is O of n. Now, this gets into binary search. So the way we do that this is handled when we use trees in actual data structures is that we use the chapter that we don't really have the time to go over, which is even in a normal semester, which is chapter 9. And that is, I normally go over it just a tad, but we don't have time for that this semester. But essentially what we do is we do self-balancing binary search trees, which means that basically that if it gets unbalanced, the tree has a way, of automatically balancing itself. So say red, black tree this is the typical, so the red black tree is the like archetypical data structures tree. And the key to any self-balancing binary search trees, the way the insertion and deletion work, is that so long as the tree was balanced before the operation we did made it unbalanced, rebalancing it takes log n time. So it takes log n time to insert something that makes it unbalanced, and then takes log n time to rebalance it. So that takes overall log n time. And so these guys have specific rules, and then the operations, basically, you have 5 cases when you insert or something, and then 5 cases when you delete. But basically, it just has these rules for making sure that basically being able to detect when the tree is unbalanced. Another one is the AVL tree, Alsavelsky and Landis tree, which builds it and swaps things appropriately. So, going back to this last question over here, and then I'll let you guys go. The equals method. Given 2 trees, check if they're equal. Okay? And by equal, that means we care about both the structure. Right method that returns whether or not the contents of the tree are identical. Do they have the exact same data in the exact same way? So not just do they have the exact same stuff. If they have the exact same stuff, the easiest way to check it, by the way, if all you care is do these trees have the same stuff, is string L is equal to in order. Assume in order gives you a string representation, in order representation of this. If all you care is do they have the same stuff, then this is really all you need to do. And then check if A and B are equal. If that's so, but if you care about the structure, then it becomes a question. So first off, we have to ask ourselves. There's four. Normally, we ask ourselves. The first question we ask ourselves is the tree we have null? But we have two trees here, so we have to ask ourselves something slightly different, which is, what are the combinations of nullness, right? So we can have tree A, so they can both be null. If tree A equals null, and tree B equals null, and I know I typed it wrong. But if they're both null, guess what? They're equal. I'm going to do else ifs just in case. Else if one is null and the other is not, then by definition, since we care about the structure, if one has something where the other doesn't, then we are going to return false. Right? The left has something but the right doesn't, or the right has something but the left doesn't. Return false. Okay. Finally, what they both are the same. In that case, if tree, first we have to check if the data matches. If tree A dot data not dot equals tree B dot data, because we care about the data contents. If their data is not equal, then the entire structure of the tree is not equal, so return false. I'm sorry if I'm going very fast on this one, because I know some of you might have class. Otherwise, they're equal. So now, what we have to do is return tree A dot left equals tree A dot left tree B dot left. Check if the left subtrees are equal, and check if the right subtrees are equal. Alright, that's that one. Alright, final, so that's the stuff for the practice exam. If you have more specific questions, I'll be happy to address them on Wednesday. There will also be time for demoing stuff on Wednesday. Also, the exam is Friday, not on Wednesday. Also, if you haven't yet, I highly suggest that you join. If you've got an idle computer that's not really doing something, get your computer running, folding at home. Yes, definitely. I'll post this lecture, and I'm going to post the other lecture that I didn't post, the guest lecture. So, but if you've got a computer, you should run Folding at Home, because because some of the efforts at Folding at Home are helping with the coronavirus effort. Like if we check over here on my local computer, which has been running Folding at Home basically since, I don't know, Friday or something, because I should have been running it earlier. Let's see. I don't know why it's not currently folding. But some of these details were on the but some of them they do help with the research on coronavirus. So, if you want to feel like you're doing something, that's one way to do it. All right, stop share. Okay, I'm going to go ahead and post this meeting. All right. So have a good day, and I'll see you in office hours at 3 o'clock.